Greetings and welcome to the latest event in the Business Matters webinar series from Gies College of Business. I'm Amanda Brantner, Senior Associate Director in Online Programs here at the University of Illinois Gies College of Business. I look forward to spending the next hour with each of you. Our faculty experts have developed this series of webinars to address some of the pressing issues businesses face today, from the economic impact of COVID-19 to cybersecurity and ethics. These webinars enable you to be better prepared to succeed and thrive through any number of challenges. Before we get started with data science's first mile and last mile problems, drivers of success for data-driven decision-making with Associate Dean Robert Brunner and Deloitte's first Chief Data Scientist, Jim Guszcza, I want to offer a few housekeeping items related to the Q&A portion of today's session. Please submit all of your questions via the Zoom Q&A feature. Your questions will be submitted publicly for the whole audience to see. In order to develop consensus around our questions, we invite you to use upvoting. The upvote thumb is located next to the question in the Q&A window. Any general housekeeping questions will be answered by our team working in the background. Any questions submitted via chat will not be taken. Today's moderator is Robert Brunner. Robert is the Associate Dean and Chief Disruption Officer here at Gies College of Business. He joined our college in 2017 and also serves as a professor of accounting and director of the University of Illinois Deloitte Foundation Center for Business Analytics. Robert previously worked in the University of Illinois Department of Astronomy, the Beckman Institute, Department of Statistics, and Informatics Institute, among others. Robert holds a bachelor's and a master's in physics from Purdue University and a master's and PhD in astronomy from Johns Hopkins University. Welcome, Robert, and over to you.
Sorry, having trouble unmuting. I wanted to first say Happy Star Wars Day. Of course, it's May the 4th be with you today. And I can't think of a better topic or a better person to share this conversation with than my friend and colleague Jim Guszcza. As Amanda intimated at the start, Jim has been a data scientist for, well, I don't want to date you, Jim, but well over 2 decades. He's the first
I started when I was 13.
Yeah, he's the first person to be designated Deloitte's U.S. Chief Data Scientist. He's been thinking a lot about hybrid human-machine systems. And in recent years, he's spearheaded the application of what's known as behavioral nudge techniques to more ethically and effectively operationalize machine learning algorithms. And I'm sure he's going to have a chance to talk a little more about that today. He's a former professor at the University of Wisconsin-Madison School of Business. He holds a PhD in philosophy from the University of Chicago, and he serves on the scientific advisory board of the Psychology of Technology Institute. And I've known Jim now for a few years. It's always a great pleasure to talk to you. And I know that this is a topic you're passionate about. So let me just start, Jim, with the following question. Data science, and we both taught data science. We both taught data analytics in many different settings. And it's often hyped with this focus, both in the classroom and in the media, with that focus on artificial intelligence or AI. What do you see as the main concerns this attention or this focus brings to the field in general?
Yeah. All right. Thanks, Robert. It's great to be here, by the way. And I should say, I am the first guy to be designated Deloitte's U.S. Chief Data Scientist. It is true. I'm on leave right now from Deloitte, and so I'm really speaking for myself, not for my former employer. I don't know how concerned I am about it. AI is just kind of like a tagline. Like 10 years ago, actually, when I was at UW-Madison, I first heard the term big data. And I was kind of similarly concerned about big data because it's just like this vague term. Actually, even when data science became a tagline, I actually kind of loved it, but I kind of hated it at the same time. These are all sort of like vague terms that are good in the sense that they're kind of umbrella terms and encompass a lot of things, which I think is really great because I think being interdisciplinary is really important to what we're talking about. On the other hand, they can kind of they can almost encompass too much and kind of give you the wrong impression of what we're doing. So with AI, some people call it the new electricity. That's Andrew Ng's quote, and that's like a way of telegraphing the idea that this thing called AI is going to transform our economies and our societies in more or less permanent ways. You know, there's a thing that economists call general purpose technologies. And earlier examples are the printing press, the steam engine, the mainframe computer, and now they're saying AI is another one of these general purpose technologies. And in the same way that, you know, when electricity came online 100 years ago, people could kind of imagine it was going to change everything, but they couldn't quite say exactly how. Maybe that's where we are right now with this thing we call AI. So we sort of need a tagline like AI to kind of connote all these kind of big fuzzy things that are happening right now. And other people call, and I'm going to quote Michael Jordan at UC Berkeley's this very famous machine learning professor. He said that AI is an intellectual wild card. And he said that because it's so vague, not only, it's not the case that like the experts know what they're talking about, but the general public is confused. He says even the experts are confused, right? And Jerome Lanier at Microsoft Research, he goes so far as to say that AI is not a technology, it's an ideology. And this is where I kind of get confused, is the ideological aspects of it, because AI originally, when it was first introduced in the 50s by a mathematician named John McCarthy, who's one of the founders of AI, their aspiration was essentially to implement all of human cognition in machine form. And back then in the 50s, it seems kind of crazy now, and we could go into it if we wanted, but back in the 50s, with the scientific air these guys were breathing, they really thought that by 2001, we'd have machines like HAL from 2001: A Space Odyssey. And in fact, Marvin Minsky, one of the people that founded the original, or one of the people that founded the field and attended the original AI conference with John McCarthy, he actually advised that movie, because these guys all thought we'd have sentient, generally intelligent computers, AIs, by 2001. That never happened. There was an AI winter. So when I started my career as what we now call a data scientist, I didn't even at all connect what I was doing with AI, because I just thought it was this kind of weird thing that was just never going to work out. I thought of it as like Douglas Hofstadter, Gödel, Escher, Bach. But now what we're talking about is called AI. So it's got this kind of like double meaning. On the one hand, it's like we've got these, data scientists are able to create machines that can do things that before could only be done by humans, like predict who's going to default in a loan, or recognize a face, or recognize a spoken word and translate to a text, right? Or, that's amazing. That's a certain kind of narrow AI. But I think it's kind of conflated with this idea that the machines are taking on a life of their own, and we're going to need less and less human involvement to build these things. And so now people are talking about the automation of data science, or using AI to automate data science, and that's where I get really, really concerned.
Yeah, I think that's very well said. I mean, one of the things I think people latch onto a lot, and by people I mean general people, not people working in the data science community so much, is this idea of machines replacing humans.
Yeah.
And I know you and I have talked about this a lot. Obviously any technology that comes along has the potential to replace jobs. I think one of the things we've seen a lot in terms of the popular press claims, and even from sort of experts in the community, is the idea there's going to be a lot of job creation going along with this, and that there's going to be changes coming about because of it. And I wondered if you wanted to share a few thoughts about that, and how people might want to think about AI as a job creator, and how that might require thoughts about, how do we prepare for this future where it's going to be a little different than before, and we're going to have to maybe pick up some new skills, and what are things that are going to be really important?
Okay, well, I'm going to give just a couple of kind of general examples, but then I'll actually bring it back to data science. By the way, Robert, is my...
Jim, we are having some issues hearing you. Could you please turn your video off? That should hopefully help things out. If you turn your video off.
I actually switched Wi-Fi networks, which might improve things. I'm at Stanford University, by the way, which is like the heart of Silicon Valley. And well, then I'll leave the rest of that sentence unsaid. No, I'll give a couple of examples, Robert, to your question about the kind of future of work and so on. And I'm going to bring it back to data science, because what you said early on was kind of interesting. It's like, well, data scientists themselves, or people that do this kind of work, maybe they're kind of sophisticated about this. But what about the more general public? But remember what Michael Jordan said, even the experts are confused. True. So I actually gave a talk a couple of years ago on the future of work for data scientists. And let me kind of like first say a few words about other professions and then loop it back to data scientists. But just to leave you on the edge of your seat, I quoted a KD Nuggets survey, that was filled out by, several hundred data scientists, maybe a bias sample, we can talk about data generating processes later. But a large number of the respondents, like I think greater than 50%, I think the question was something like, all of the major aspects of your work will be automated within the next 5 to 10 years. And a surprising number of people said, yeah, that's probably going to happen. In other words, the major parts of data science are going to be automated. Now, people listening, just think about, do you agree with that or not? And we'll come back to it. And I wish I could do a poll to see if I could change anybody's minds about that. But I just think about very simple examples, like there's this very simple example that labor economists use about what happened with for the demand for bank tellers after ATMs were introduced. So ATMs, by the way, I would define as being a form of artificial intelligence. A lot of AI people like to define human intelligence down to pretend that AI is going to replace humans. I like to define AI down to include not just deep learning algorithms that flag tumors and x-rays to help radiologists. And there's a lot of talk about those things replacing radiologists. Well, no, I would define narrow AI, the kind of AI that we're talking about that's really getting into the real world, is being any technology that can perform an operation that used to require human involvement. And I'm sorry, that would include what people in consulting call robotic process automation, building a macro to do a well-specified task, a task that requires just explicit knowledge you kind of codify. So that's kind of what an ATM machine is, right? I mean, that was introduced several decades ago, and can do all these operations that 30 plus years ago human beings did. If it's a yellow check, do this. If it's a blue check, do this. Here's a deposit. Here's a withdrawal. You can kind of write all that stuff down. You just mechanize it, and this happened. And so, what do you think happened for the demand for bank tellers after those things were rolled out? 1, 2, 3. The demand went up, and the reason the demand went up is because it became more economically expedient and possible for banks to open increased number of branches. Right, you don't need as many humans manning the branches, so it's more of an economic advantage. But you couldn't just have a purely automated branch. You had to have a couple of humans there working next to all those ATMs just to kind of answer common sense questions. And so that's the reason why the demand went up. So the point is that if we have technologies that have complementary skills to what humans have, then the more of those technologies are rolled out, the more demand there might be for the humans with the complementary skills. It's kind of like the cheaper hot dogs become, the more people want to buy hot dog buns, the demands would kind of go up. Yeah. Okay, and the point was that the jobs didn't go away, the jobs went up, but the jobs changed also, and the jobs became a little bit more like customer service and a little bit less like kind of mechanical. Okay, I'm going to do this with these checks. And so
what you're describing, Jim, is really the sort of blending of the best of humans with the best of the machine. Yep. Right? And I think that's something that's very important and often glossed over here, that together they actually bring a lot of strengths and mutual synergies.
That's exactly right. No, it's like, just think about, working with humans in a workplace. Like if you're, working in a consulting firm, or if you're working as a doctor in a hospital or a professor in university, Robert, if you've got a bunch of, really young teaching assistants who could like kind of outsource, that you can outsource with some of your work to, would you say, oh, therefore we don't need professors anymore? That's about as logical as saying, oh, we've got these deep learning algorithms that can flag tumors better than the human eye can. Oh, therefore we don't need radiologists anymore. That's just the complete non sequitur. Yet some of the top minds in deep learning tweeted and have publicly stated and almost doubled down on exactly that. I think some have changed their minds, but there's at least one example of somebody who really doubled down on that statement. I think it's just a non sequitur. So just as with teams of humans, cognitive diversity produces what Scott Page, University of Michigan, calls a diversity bonus, then we can think of that along the same lines. Just these are very narrow but deep, quote unquote, intelligences that complement humans. And this actually goes back to an interesting scientific finding from 60 plus years of AI research, which is really, really interesting. Initially, those guys back in the 50s, John McCarthy, Herb Simon, Marvin Minsky, and so on, they sort of assumed that if you could get computers to play chess or prove theorems or win at Go, those are the hardest things. Those are the things that only the officially smart few can do. So if you can get computers to do that, well, duh, of course they could recognize a face. But it turned out that the things that are actually most easy for people, like using common sense or forming a hypothesis about what's going on, those turn out to be the things that are hardest to get machines to do. So in AI, that's called the common sense reasoning problem. And hype notwithstanding, there's no real indication that that's going to change anytime soon. So this idea that we've got these like very narrow but deep intelligences with no common sense, but humans that have a hard time memorizing things, they have a hard time making the same decision before lunch versus after lunch. It's a topic of Kahneman's new book that's coming out. But they have common sense and they can form hypotheses. They can understand context. They can like handle edge cases and exceptions. The natural thing is like, let's bring them together, kind of like the tellers and the ATMs.
Yeah.
We can turn that, we can flip that over to the data science conversation if you want.
Well, I think that's a good segue to what I wanted to sort of explore next, and that is, and I teach data science here at the Gies College of Business, and
Yeah.
one of the things a lot of people do when they're teaching data science is you focus a lot on the the algorithms, what algorithms are using naive Bayes, k-nearest neighbors, regression, whatever, feature selection, performance metrics. Now, is that the right approach now, or even into the future as we see increasing automation?
Yeah, that's a really good question. I mean, I think my kind of answer is going to be sort of not really. Honestly, Robert, I've taught data science boot camps for a long time. I've taught you're the more outgoing of the two of us, by the way. I was trained as an actuary, and you're an accounting professor, so you're the more outgoing. So I'm a bit,
But I'm a physicist, not an accountant. So
okay, well, then even more. But I've taught data science boot camps for a long time. I've taught. I started doing this in R like back in the mid 2000s. I would teach 2 or 3 day boot camps to kind of working actuaries, and just the kind of basics of both kind of programming with data, but also fitting classical statistical models like generalized linear models, but also machine learning models. I've always had a lot of fun doing it. I might do it again this summer, in fact. But honestly, I always kind of thought to myself, in fact, I would explicitly tell the students this. I'd say that there's this kind of pipeline of what a real data science project looks like. This is before I called it the first mile problem, the last mile problem. But what I'm teaching you in this 2 or 3 day boot camp is right smack dab in the middle of it. This is the easy stuff. And honestly, it's the easy stuff to teach. It's the stuff that is most amenable to classroom discussion and writing textbooks. And going back to the ATM thing, really a lot of the stuff we're teaching is sort of like explicit knowledge. Okay, there are these rules of thumb, split the data 60-40, or do cross validation, and fold cross validation, or for these kinds of problems, you want lasso regression. For these kinds of problems, maybe a deep learning model. For these kinds of problems, maybe decision tree kind of thing, ensembles. These are all things that you can kind of like, they're so amenable to instruction that ironically, those are the aspects of data science that are most automatable, right? And I always kind of felt that. And I'll tell you a little secret. Early, these guys are all retired now, so it doesn't matter. Early on when I was teaching my data science boot camp, there was controversy about I was giving away all of our trade secrets by doing this. This is years before the term data science came online, and we pioneered the application of using machine learning to help commercial insurance underwriters better select and price risk. So it's very exciting, and we don't want to give away our secrets. But I made the case, some of us made the case that this is the stuff that is textbook knowledge, right? The real secret is the tacit knowledge, right? It's really kind of understanding the data. Where did the data come from? The strengths and limitations of the data. And then the last mile problem is, what do you do with it? How do you integrate that with business systems or with human decision makers or with a greater society? Are there all these other issues? And so, the part that is easy to teach is the stuff that is most amenable to automation. And the stuff that is necessary and doesn't get taught as much, I call it, you're a physicist, so I call this the dark matter of applied AI. It gets 20% of the attention, but it counts for 80% of the success. And that's not to say that we don't need to go to data science boot camps or take classes in data science. You absolutely have to, right? But just be aware that just doing that alone is not enough for success. And I think that a lot of the negative headlines about AI that we're seeing in the papers is due to sort of like a narrow framing of AI and machine learning in the minds of practitioners and business leaders, and maybe even some of the critics. And I almost think that because of all the hype around big data and deep learning and machine learning, people are anchoring, they're doubling down on that 20%, right? The stuff in the middle, and they're forgetting about the first mile problem and the last mile problem. And
it's funny. Actually, I'd probably argue with you that the 80-20 is probably being generous to the algorithm importance, right? I mean, it might even be 90-10 or less. But the funny thing there is that we keep harping on that, and as you say, it's the easiest thing to teach, and yet in the end, it's going to be the most automatable. It's going to be the part where, at best, you have to understand those concepts like the algorithm choice, the feature selection, so you can explain what
Right.
the model's doing and
Yeah.
explain to people why the performance is what it is and why
Yeah.
it may not get better no matter what you do, unless you get entirely new data or whatever. But that leads us back to this first and last mile, which is kind
Yeah.
of the point of this this webinar. So let me, I know you like this quote from John Tukey, one of the maybe
Yeah.
the original father of data science. And that is,
Yeah.
an approximate answer to the right question is worth a good deal more than an exact answer to an approximate problem.
Right.
Why don't you explain that quote and its relevance to the first mile?
Yeah, I mean, we're not trying to build an elegant algorithm. We're trying to get a better outcome. Okay, that's the idea. So if you don't figure out, what the right a narrow way of interpreting Tukey's comment, right? An approximate answer to the right problem is more important than an accurate answer to the wrong problem. A narrow way of interpreting that is, if you select the wrong target variable to predict, you'll just get something that's not going to achieve your goals, right? Intelligence is about achieving goals. That won't be artificial intelligence. That'll be artificial stupidity. An early example from my back pages, this is going way back to the beginning of our practice, was, we were trying to build algorithms to help in commercial insurance underwriters select and price better risks. So, for example, Robert, if you own a cafe in Champaign, Illinois, and I'm the insurance underwriter, I show up at your cafe and I say, oh, I like Robert, oh, this is good. Yeah, it looks pretty good. It looks well run. So I kind of let a lot of, intuitions guide my judgment. And what we learned early on was that if we build an algorithm that kind of anchors my judgment and something a bit more statistically grounded, I will tend to make a much more economically profitable decision for the company. It'll be a more accurate assessment of Robert's risk. This is a pretty straightforward, like early data science, right? But because we were competing with firms that were more steeped in traditional actuarial methodology. And they were just kind of starting with like the algorithms, and they were saying, well, gee, insurance is about frequency and severity. And so for frequency, we need to kind of fit a logistic regression model to say, is there a claim or not? And for severity, we'll fit like a log normal model on the severity part of it. And we're kind of like, guys, we're not trying to predict the potential dollars of loss, from Robert's, risk if we underwrite the policy. Rather, what we're trying to do is say, would this be profitable? In other words, like there's already a premium that's sort of like the sticker price for Robert's risk. It's based on how big his restaurant is, what type of business is, and so on. The premium is already out there. We're not trying to estimate the premium. We're saying, given what the premium would be if I sold an insurance, how would the loss be? So we want to bring the price in as well as the expected dollars of loss. But our actuarial colleagues, because they think so hard about like what's the right way to estimate that premium in the first place, they mistook that. So we would literally be hired by people that had first gone with some of our competitors, and they simply predicted the wrong outcome, and it was just worthless to their company. They just couldn't use the algorithm, right? Or another time, this is us. We built an algorithm for another client, and I won't give you the domain, but it was intended for use with kind of existing cases. And the client, we didn't realize it, started using it for new cases with no history. Again, they were using the algorithm in a way that was not intended. And I'll give you a more recent example, which made all the headlines. Amazon famously built a predictive algorithm to streamline its hiring process. All right. And what you want to do is you want to kind of say, well, we want to help automate or streamline or facilitate the hiring of successful employees. Now, going back to Tukey's thing, we want an approximate answer to an imprecise question, not an exact answer to the wrong question. The imprecise quantity is, well, what is a good employee? Who knows what a good employee is? That's not a thing in the world. That's what social scientists call a social construct. You just kind of got to sit down and hash that out with your clients or with the greater society, right? There might be a political dimension to this too, to kind of agree on what does a successful employee look like. What these guys did, and I'm not trying to blame anybody. This is just kind of like, I just think of this as being a parable that kind of like summarizes a lot of kind of what happens in the real world. They just said, oh, okay, well, we'll just like, we have this historical data set, and we knew who was hired and who wasn't. So we'll take that outcome variable, who was hired, and we'll regress that on a lot of features that we extract from resumes. And I think many of you probably read the headlines. What happens was they got an algorithm that was biased against females. So if your name is Brandon and you played lacrosse, you're more likely to be flagged as a potentially successful employee than if your name is Melissa and you were the head of the local chapter of Girls Who Code, right? So they got a gender biased algorithm, and they never used it. They pulled the plug on it. And that's kind of where the story ended. And I think they missed the good part of the story. We could talk about that later. But the point is that just completely So John Tukey was this kind of legendary pioneering figure back actually in the 50s. He was friends with some of the pioneers of artificial intelligence. And by the way, he was friends with Claude Shannon. He gave Claude Shannon the idea to call a bit a bit. He coined the term bit. He coined the term software. He was also the proto data scientist. And he was one of the most quotable, thoughtful data scientists ever. And that little bit of wisdom of his completely captures what happened with Amazon. But people don't have it on the top of their mind, which to me suggests, and the fact we see so many headlines that are basically identical to that, makes me think that these types of ideas about what data science is all about are not kind of in common currency anymore the way they should be. And again, this answer of figuring out an approximate answer to an imprecise question, that requires common sense and ethical deliberation. The kind of stuff that, going back to what we said earlier, cannot be automated.
Well, you know, that example very nicely illustrates this entire concern about not understanding the first mile, because if you automate or even semi-automate the algorithm selection, you know, so it automatically says here, given this data, here's the best algorithm, here's the highest, you know, scoring algorithm, here's the best features to use, here's how well you're going to do based on your training data, then you're going to make it easier for more people to make more predictions that are to the wrong problem. Right.
That's right.
And so you're going to accelerate that opportunity. And if people don't actually have that knowledge or insight that, wait a minute, I need to take a step back and think deeply about the problem I'm confronting.
That's
and,
right.
And in some sense, bring the scientist part of data scientists to the fore.
Yeah.
You're just going to end up accentuating the problem and having more headlines, which, you know, may be good for automated algorithms that write, you know, news articles, but it's not going to help us make progress as a society. So I think that really is a great illustration of this problem. Now I know, I know one of the, I know, shocking, right, that you and I would agree on this.
Exactly.
But one of the things that comes into this, and I know you talk a lot about with first mile problem, is this whole idea of going back to the data. You know, when you think you have an understanding of what that problem is, and then starting to think about what is the data, where is this data coming from, what's the right data, how do I understand the sort of generation process that's at the heart of the problem I'm trying to solve, if you really want to think about it, right? How do you describe that data generation process, and how do you bring that into conversations with people who may not be experts?
Yeah, it's like, you know, I had a kind of a light bulb go off when I read, if you guys haven't read this, you have to go, your homework is to go and look this article up. There's this classical article by Leo Breiman called Data Science to Two Cultures. Leo Breiman, I'm sure all of you know, is the guy who invented the classification and regression tree algorithm. So he kind of, you know, really made the mathematically precise decision tree algorithm. And he of course came up with the random forest algorithms and so on and so on. Extremely thoughtful guy. And he basically said, look, there's this pendulum that's too far on the side of this kind of data modeling culture. In other words, like, you know, statistics back then, what I started with, like, we'll assume the data is Gaussian or assume the data is log normal. And he's like saying, what are you talking about? We don't know what a Gaussian, you know, we can't observe a Gaussian distribution. All we have is this pile of numbers in a spreadsheet in front of us. Get real, guys. We need to be able to work on this data. And he said, we need more of an algorithmic culture in statistics. And he was kind of talking about things like random forest and CART and boosted trees and stuff like that. And I think the kind of culture has kind of gone way too far to the other extreme. And actually, one of the people who commented on Leo Breiman's essay was David Hand, who's at Imperial College London. David Hand has a new book out called Dark Data, which is essentially about what we're talking about right now. The idea of dark data is like there are a lot of patterns actually that you want that are not in the data. You might have sensor data. So going back to your happy employees, well, the unhappy employees left the firm. All you have left are happy employees. If you just analyze the people in the firm, you're missing the dog that didn't bark, right? Or if you're Amazon and you've only hired men before and you don't have a very female workforce, well, you might want to think about that data generating process, like past hiring decisions. Those are the decisions that generated the data. You might want to think about the fact that if there are human biases involved in that process, right? If it's men doing most of the interviewing, there's this thing called affinity bias. You hire people who are like you, who played lacrosse, not were part of Girls Who Code. And you're not conscious of it, it just kind of happens. It's not like you're a bad person, but that's thinking about the data generating process. Now, I always go back to my humble, incredibly primitive experiences when I first started as an actuary in the Midwest. And I was doing loss ratio calculations on the back of a shovel using chalk. But when I showed up, you know, at my company, and they sat me down in my beige cubicle, and it was like a scene from Office Space, and, you know, we didn't even have a red stapler. And they literally told me I was lucky to have my own telephone. And I had a computer that had Excel and Access, and Access was for the advanced stuff. And my heart was broken because I didn't actually know what an actuary was. I assumed at the time in my naivete that an actuary is what we today call a data scientist. And I was really kind of heartbroken. Now the story ended really well. I mean, 2 years later, I was fitting the company's first credit scoring algorithms, which was a lot of fun. But my point, and I do have one, is that the stuff we were doing was actually first mile problem stuff. Because when we were trying to figure out, how do we come up with a new price? How do we decide how much more to charge for young men than older females? How do you do that? Well, you take a lot of past data and you figure out, how much more losses per hundreds of dollars of premium did the men have versus the women. But the thing is, if you take data from last year and from 5 years ago and from 10 years ago, there were rate changes in the middle. And maybe medical inflation went up, that would change the severity. So there are all these ways in which a data point from 1 year ago would be different from a data point from 5 years ago versus 10 years ago. We spent all sorts of time obsessing over those changes. And I thought, oh my God, this is so boring. I made such a mistake, entering this profession. But the perspective it gave me was that this is like John Tukey. That's more important than the decision, which is more fun to talk about and easier to teach. That is more important than the decision about should I fit a logistic regression model or a probit model or a Poisson regression model or even an ordinary least squares regression model. A lot of these things are very robust. And you actually sometimes want to use a simpler algorithm than a more complex one because you don't want to overfit an imprecise data set. We talk about that too. So, but that's like a very humble example of thinking about the data generating process. Now, fast forward to 2014, and I was very honored. I was asked to give this centennial keynote talk to the Casualty Actuarial Society. It was like their annual meeting, was like their centenary celebration. There were 1,000 people in the audience. I was terrified. It was the biggest audience I'd ever spoken in front of. But I was talking about Google flu trends. And Google flu trends had recently failed, okay? You guys might know about this. Google had this brilliant idea, truly brilliant idea, which actually relates to kind of using data signals for tracking COVID outbreaks. But they were saying, look, the Centers for Disease Control have their time series methodology for tracking flu outbreaks. Google can do the same thing, but in real time rather than waiting for the lag statistics. Because if I know there are a whole bunch of people kind of like typing in feel sick, cough syrup, doctor appointment in Champaign-Urbana, in Champaign, Illinois, well, there's probably a flu outbreak in Champaign, Illinois. So we know that in real time. And they call that predicting the present, or nowcasting, right? And so they built this flu tracker, the Google flu trends algorithm to predict flus in real time, or kind of nowcast, predict the present. And it ended up, I think, on the cover of like Nature magazine or Science, one of the two. Really big deal. And it was a poster child in the book Big Data by Kenneth Cukier, editor of The Economist magazine, big best-selling book. It's poster child for this new paradigm of data science, right? Or of science. We don't need to worry about causality. All we need is correlation in big data sets. There's actually a Wired article that said this, saying, Google teaches us the scientific method. We don't need it anymore. It's kind of outlandish. But in 2013, 2014, I think that's earlier that same year, Google, well, actually probably 2012, 2013, Google flu trends stopped working. It started over predicting flu outbreaks. And there's a second article, Google flu trends, what went wrong, in the same journal, Nature, written by David Lazar, Gary King, and many other really prominent scientists. And they basically said the problem was twofold. One was they weren't thinking about the data generating process. Google is always updating its search algorithm, right? And that means that the denominator of these ratios, percentage of the bag of words dedicated to flu outbreaks versus all the searches, that changes just because the denominator is changing. And I said, if actuaries had actually stepped up to the plate and become like more mainstream data scientists who were kind of doing this kind of stuff in the larger world, just think to yourself, would we see as many of these mistakes? And I'm not trying to say actuaries are great. I'm just saying that all that, actuaries are really boring people. But all that boring stuff that they do, there's actually a reason for that. And a lot of that kind of traditional wisdom is being sort of like ignored, or maybe never even taught in the first place, to a lot of people who think that a data scientist means the science of managing data, not science using big but incomplete data. So the second part of their diagnosis was, it wasn't just that they ignored the data generating process. The more general diagnosis was big data hubris. The idea that big data is a substitute for, rather than supplement to, more traditional modes of analysis, like those like boring actuarial things I was talking about. End of another rant. I hope that was useful.
No, it is, and I think you that Google flu, the whole prediction and controversy that surrounds it really highlights that if you don't understand the basics, you're bound. What is it? If you don't learn from history, you're bound to repeat it.
Yeah.
Right. And here we see that, of course, causation matters, right?
Right.
If you're not learning what's causing, why to go up, then you're really doing the wrong thing.
Yep.
And and yet a lot of people did jump on this big data as a salvation, because we just collect a lot of data, let the machine learn from it, and it's going to tell us
Right.
patterns that are important. And
Right.
the issue is the machine can't say whether something's important enough, right? It
Right.
might be able to say it's statistically, relevant, but it's not going to be able to say that this is important, because that's got to be
Right.
the human has to come in and sort of do that judgment.
Exactly.
And I think that kind of leads us into the second part of this topic, which is really the last mile problem, right? In some sense, we talk about building the model, assuming we've got the right data, which is,
Yeah.
as we just discussed, a big if. Assuming we have the right data, what is the sort of issue then when we built our model, right? Building the model is the easy part of the problem.
Mhm.
What are the issues that we really have to worry about, when somebody, say maybe it's our junior colleagues who haven't as much experience as us, and they come in and they build a model and they bring it to us. What are some of the things that you would immediately be worried about or think are concerns and need to have further discussion?
Yeah, well, just summarizing what we said earlier, I would worry about first mile problem types of issues. Are we predicting the right outcome variable? Are there any kind of hidden assumptions there, or are there kind of issues that get swept under the carpet? Because and by the way, people are not stupid.
Yeah.
People are not ignorant. People are working in organizations that have time pressures, right? And there's people have serious. So you might hear me say this, and you're like, yeah, what Jim says makes sense. But you know what? When you're in the pressure of trying to turn out product, and Robert, you made this comment to me earlier. This is why it's kind of on the top of mind. That sometimes short-term pressures kind of crowd out deliberation about these things. There's a famous experiment from psychology. Christopher Chabris was one of the psychologists who did this. Maybe you've seen this. You're looking at a bunch of people who are kind of trading basketballs, passing a basketball off from one to another. Okay, you got 5 people, and they're all kind of passing basketballs. And someone asked me, Jim, count up the number of times this basketball changes hands from one person to another. I'm counting. I'm trying to make it be as precise as possible, right? I'm trying to do this predictive algorithm under this time pressure and get all these hyperparameters correct. And during the experiment, no kidding, a guy in a gorilla suit walks across the basketball court where people are passing the ball. And then you ask people, did you see the guy in the gorilla suit? And they're like, what guy in the gorilla suit? And that's actually a parable about human psychology, that human attention is more like a spotlight than a floodlight. And when you're driving while texting and you think you're paying attention, no, you're really just texting. We are strangers to ourselves. We don't really understand that about ourselves. All right. So this is why, smart people can do kind of dumb things, or good people can do really evil things. Okay. So it's we need to change our organizations too. So yeah, I would kind of look at all those kinds of questions about assumptions that were made in either the rows in the data set. Did we get that sample right? Are there enough? Did we oversample females or neglected classes, for example? In insurance, if we no longer write these policies, why would this be here? Or I'll give you another example from my back pages. Once we were building an algorithm for a hospital system to predict which doctors are high at risk of getting sued for malpractice, a colleague passed off the project to me when he was going on vacation. And I loaded the data in R and analyzed it, and I realized, oh, he included nurses in the data set, and he included a nurse indicator variable in the machine learning parameters, which had a really negative double-digit parameter because nurses never got sued for malpractice. So I'm like, okay. So pay attention to the rows in the data, that sampling frame. Nate Silver, he underweights or overweights, different polls depending on their past history. That's kind of paying attention to the sampling frame, but also the target variable, Tukey's advice. But I would also kind of pay attention to how operationalizable is it? I've learned to say that word. Is this actionable? So if we're predicting which employee will be a good employee, like Amazon was doing, assuming we answer all those questions in a satisfactory way, great, I can operationalize that. Because if I'm interviewing 30 employees and I only have 5 positions, well, I can at least, allow those 5, top scoring, who got the 5 top scoring scores. Maybe that won't automate the decision, but maybe that will improve the decision, kind of like my underwriting thing. Or if you've seen the movie Moneyball, that's a Moneyball application of algorithms. Okay. On the other hand, I've seen people build algorithms to predict which employees are likely to quit. And he was like, okay, we know who quit, regress that. And that's very convenient. You've got all the data there. But what are you going to do with that information? How is that actionable, right? So there's another great maxim, not from John Tukey, but from Don Rubin at Harvard. And he said, suppose there were no uncertainty. Suppose you didn't even need statistics. You just had a crystal ball and you could know which employee was going to quit. What would you do with that information? If they're going to quit anyway, maybe it's not actionable. So what you really want to know in that case is it goes back to the causation correlation thing. Who are the people who would quit or will quit or are more likely to quit if I don't intervene in some way? Because there might be some people who are going to quit no matter what they're going to do. They have to move, So again, I'd want to look at all that stuff. And Robert, we can talk about the last mile problem and this idea that ultimately we don't care about the algorithmic output. We really care about the business outcome that kind of gets to this idea of, acting on the information.
Yeah,
so
I
can talk about
think that's I think that's a good point to consider, because in particularly in classes when we're teaching data science, we go through that. Even if we've talked about some of that first mile, what do? We say here's the approach, right? But in reality, when you're a data scientist and you're working on the problem, you're taking some data you have, you're doing all those typical feature selection, algorithm selection, using performance metrics, trying to make that prediction. And then you're turning that over saying, look, we've made this prediction as requested. We're doing this result. But that has to get actually implemented, or as you said, operationalized by probably other people in the organization. And when that hits new unseen data, real world data, there does need to be some reconnection back into the process, right? So in some sense, that last mile is really coming back in and telling you what you might have not appreciated or might not have seen or might not have, or maybe even what you missed in the first mile because you didn't think about things deeply enough. So what sort of advice or thoughts might you have around that whole idea of you've operationalized it? What can you learn and how do you bring that back into this process? What are some things that might happen that people aren't aware of?
Yeah, okay. And before I answer that question, let me just to kind of anchor everybody again. I'm not sure how clear I was even defining these things. When I say first mile problem, it's kind of like realizing ultimately we're not trying to model a data set. We're trying to model something that comes from the world. And there's a difference between the data set and the world that generated the data. So that's ignoring that is kind of ignoring the first mile problem. That requires human judgment, can't be automated. The last mile problem, on the flip side, ultimately why are we doing this? Are people paying you life is not a casual competition. You're not getting paid to create the most accurate output. You're paid to facilitate or be part of a larger process that results in a better outcome, right? We care about, did the patient get healthier? Is the diagnosis more accurate? Did our workforce become more effective and more diverse? Is my overall combined ratio, if this is an insurance company, more profitable? So that's bridging that gap between the algorithmic output and the outcome is the last mile problem. So I think that the answer to, or a big part of the answer to both of these things is, this is not a term that was in my vocabulary early on, but there's this term that a lot of people have called participatory design, which is what we did early on. The reason why I'm still here to talk about this, the reason why our practice did not fail, and the reason why it continued to make money before all the hype around big data and data science and AI, was because we just instinctively knew this is the right thing to do. We had to kind of figure all this stuff out, otherwise we wouldn't have survived. And so we were very clear on the fact that if we're going to build an algorithm for all these underwriters to use, we're going to get a very well-respected underwriter in the organization to help us think through all the data, or a fraud investigator, or a doctor, whoever this is, or a child support enforcement officer. We're going to work with those people to understand what is the nature of their decisions, what kind of prior knowledge do they have, and again, knowledge is different from information. Information is different from data, right? But we would take their kind of hypotheses about, doctors who went to, a foreign medical school, they're actually less likely to get sued for malpractice. It's counterintuitive, but here's the reason why. They had a causal explanation. We would hear that during the feature generation process. We'd have those conversations about what target variable we try to optimize. Mm-hmm. Delinquent means, they've done less than X% within X number of days, that kind of thing. So that on the one hand, that gives you a better algorithm, but on the other hand, it gives you, so it addresses the first mile problem, but also it helps address the second mile problem, because there's this thing called algorithm aversion that psychologists have begun to study. Again, if you've seen the movie Moneyball, algorithm aversion was kind of brought to life by the Philip Seymour Hoffman character, this skeptic, right? He was the baseball scout that thought, this is just ridiculous. There's no way that this little predictive model can replace my years of wisdom. We experienced that exact same thing in the early days of our practice. And this goes back, and this is still a thing, right? Doctors don't like evidence-based medicine. They won't wash their hands. They don't necessarily trust the algorithm. So algorithm aversion is a whole body of study. But in my experience, I'm not sure this has been studied formally, if a high profile member of the organization has been involved in the design and build, it's like each step of the way in this participatory design kind of thing, then the end user is more likely to embrace it and more likely to use it in an intelligent way. Okay. And do you want me to give you an example of how that went wrong?
I think learning from failure is always a great thing. So sure. Yeah.
Oh, no wonder I know so much. Yeah, no, this is kind of early on, and actually, this is a luxury because like it involved us, but we actually there's no way we can take the blame for it, because we built an algorithm for clients. We got the first mile problem right. We didn't predict claim frequency. We predicted loss ratio, profitability. So we got we did the Tukey thing correct. We paid attention to the sampling frame. We did all that boring stuff. We built a good algorithm, right? By the way, we started building neural nets back then, but we quickly dropped those in favor of generalized linear models just because it made more sense. We could talk about that if we wanted to. But we gave, this is one of our first projects, and we handed it off to our client, and they did not hire us to do any kind of change management. They just said, we want the algorithm, we don't want to pay you guys to help us implement it. And so we were nervous because this is one of the early things we did. This client was a bit smaller, so they didn't have a lot of data. So we're working with sort of imperfect data. Again, side comment, you actually can do a lot with imperfect data. Again, hence the need for more judgment, but okay. So they emailed us back 6 months later and said, you guys should feel proud because your algorithm worked every bit as well as you hoped. So, we did the out of sample validation, but the out of time validation was equally good. And that was like a big relief to us. This was like 20 years ago, right? And they said, but we lost money with it. And this is a big surprise to us. Like, how could you lose money? The algorithm worked. And I wasn't thinking about this. This is like a real learning for us. And what happened was they found that the underwriters were systematically using the algorithm to give discounts to profitable risks, or risk the algorithms that were profitable, but they wouldn't surcharge less profitable risks.
Yeah.
Right? It was like they'd only do the good news. And so this is what today I would call artificial stupidity. It's this parable about how an algorithm can be great on its own terms, but if the user does not have a good kind of mental model of how the algorithm should be used, he or she could use it in a way that actually creates artificial stupidity. Now, fast forward to like this past Saturday, there's yet another headline about some guys who were killed in a Tesla. I'm not trying to criticize Tesla, but they're killed in a Tesla, and there's literally nobody behind the wheel. That's exactly the same kind of artificial stupidity I'm talking about, where this smart machine offered a certain kind of intelligence, but that intelligence is misinterpreted by the human user, and a bad outcome existed. So my modest parable from 20 years ago and that Tesla thing from not even a week ago are both examples of artificial stupidity, because we did not bridge the algorithm output better outcome gap.
Yeah, no, I think that's tragic, but yet very good point. And I guess that leads me back, and you did kind of open the door to this. I did want to ask this sort of clarifying or follow-up question, and that is, maybe you could talk a little bit more on the focus on interventions and not just predictions, right? Typically, we think about build the model makes some predictions, and then we use it. But in this case, the focus isn't just don't worry so much about that prediction, but how do you use that to actually prove something, right?
Exactly. I'm going to just give a couple of, so this gets into ethics too, right? Like if you've got an algorithm that's being used by judges to help, predict who's going to recidivate, and we can't get into this whole thing, but like you've all heard the headlines. There's this famous example of the Compass algorithm, right? One of the most widely used algorithms to predict which people up for parole are likely to recidivate, i.e. commit another crime and have to be sent back to prison if they're released. And it turned out that the false positive rate in this algorithm was twice as high for blacks as for whites. It also turned out that the algorithm was equally well calibrated for blacks and whites, meaning a prediction of about 70% roughly means that there's a 70% chance this person will recidivate, regardless of whether the person is black or white, which is kind of counterintuitive, because wait, these are both fairness ideas, but it turns out you can't satisfy both if the overall base rate of recidivism is different for the two groups. So all I'm trying to say with that, if you didn't follow that, which you probably didn't, it's okay, although you should read up on it, is that there are these like inherent moral quandaries of a lot of these algorithms. And like, it gets you to think, what do we even do with this algorithm in the first place? Maybe we shouldn't even use it to make parole decisions. Maybe we should use it to help people avoid, a bad thing in the first place. So I'll give you a very simple example of interventions, not just predictions, and then a more substantive one from my own back pages. I keep quoting this Bob Dylan song, "My Back Pages," by the way. That's where I keep getting that phrase, back pages, from. The simple example is from Microsoft Research, the Bing search engine. And this comes from a psychologist who works with data scientists named Dan Goldstein. I'm a real fan of him. And if you type, according to this, based on this work he did, if you ask Google search, what is the area of Poland? I'll get a number back, just this big number, which I can't interpret. But if you type that same thing into Bing, Bing knows that I'm typing from the US. And so it gives me a response. It gives me that same numeric answer, which is probably gobbledygook to me, but also gives me a little message saying, oh, it's about the size of Utah. So that's a less precise output, right? It's a less precise output, but it's more useful to me as an end user. So it gives me a better outcome, because now if I'm planning a trip to Poland and I'm trying to rent a car, I've just got a better like first order idea of like, should it be a weekend trip or a 1 week trip to Poland kind of thing, right? So that's just an interesting example of like, don't just think about the algorithm output. What are you going to do with it? Don't just give them the number. Say, oh, it's about the area of Utah. Analogously, if I'm building an algorithm for doctors and it's saying, Jim has this risk of having the rare disease, don't just tell the doctors there's the probability, the algorithm is 95% accurate. Because if the overall base rate of the disease is low and the algorithm is saying 95% accurate, the doctor might think that Jim has a 95% chance of having the disease. Yeah. But you guys are all sophisticates. You know that if you look at the posterior probability using Bayes' theorem, if the overall base rate is low, the algorithm is 95% accurate. No, the probability that Jim has the disease is like 17% or something like that, right? And that's very counterintuitive. Well, actually, I had a project to work with that had this exact quandary. We were asked to build a fraud detection algorithm for the state of New Mexico for unemployment insurance. So it was insurance, but this is like public sector kind of stuff. And the idea is if someone has lost their job and they're just making a little bit of money every week, mowing lawns or driving Uber or waiting tables or whatever, just doing gig work, they're supposed to log onto a portal every week and certify, I made $150 last week. And then how much they report, well, their collection, their unemployment benefits is tied to that. So if you underreport your earnings, you collect more money. So there's this kind of like perverse incentive for people to underreport their earnings. So the current state of the art was pay and chase. If you find out downstream the person was improperly reporting their earnings, you try to claw it back from them later, which is nobody's happy with. So they hire us to build this algorithm to suss out people in real time who are highly suspicious of collecting benefits improperly, underreporting their earnings. So we built like a suspicion score. My colleagues got me on the phone to try to brainstorm what is the most accurate way to build a classifier for this. Again, thinking about the middle stuff, the easy stuff. And I said, pause, think about the first mile problem, think about the last mile problem. The overall base rate of fraud is low. So no matter how accurate we are, right? Someone even in the worst decile of our risk score will probably only have like a 20, 30% chance of being a fraudster. So if we build such an algorithm and implement it to automatically switch out benefits, we'll be withholding benefits improperly 60, 70, 80% of the time. We can't do that. That would be creating a weapon of mass destruction. I was literally thinking of Kathy O'Neill's phrase when I had this conversation. And so I said, here's what we'll do. We're going to build the algorithm, but instead of using it to automatically shut up benefits, let's propose to our client that we use it as a nudge engine. So I was thinking about Richard Thaler's book, Nudge, and Dan Ariely's books about honest behavior. Remember what I was saying before about how even good people in bad situations can do bad things? The same person who's living in Sweden and pays his taxes on time, if he moved to Greece, maybe not pay his taxes on time because the social norm is different. In one setting, you're a sucker if you do the honest thing. In another setting, well, that's just what we do. Yeah. So people's ethical decisions are based on their situation, not just on their ethical nature. So this idea of flagging fraudsters, it's not like flagging cats and dogs on the internet using deep learning. Whether somebody's going to commit fraud or not depends not just on them as a person, but also on the situation. We can change the situation. So if someone if someone scored in the worst decile of our algorithm, for the first time in all those weeks of reporting earnings, they see this little pop-up message saying, Robert, did you know that 9 out of 10 of your neighbors in Champaign report their earnings honestly? And that will prompt a little bit of metacognition, a little bit of reflection on the part of the person submitting these benefits. We A/B tested those kinds of messages online, the same way that Silicon Valley companies do. And we found that that combination of machine learning and behavioral nudge messages reduced improper payments by about 50%. And it persisted over time. So it was a really big effect size. And so rather than, there was another state that was building an analogous algorithm at the same time that is still facing a class action lawsuit for withholding benefits from people who deserved it. Whereas our solution was actually written up by Pew Charitable Trust as being an innovative use of what they call behavioral analytics. So that's an example of thinking about not just the prediction, but the intervention. The intervention should not be to shut up benefits. The intervention was just give a gentle nudge. Because if the algorithm is wrong, no harm done. You just ignore the message. But if it's right, you're more likely to be prompted to do the honest thing. So just maybe a thought-provoking example.
Well, that's actually really good because it actually hits the end goal of the client more accurately than just shutting off, which is just going to drive up, calls into the excuse me, the office and people complaining and bad press. And so there's a lot of issues there. And it also highlights the importance of bringing the human back into the entire process.
Exactly, and human judgment. That's right, and ethical deliberation.
Yeah. So I think we've hit on this a lot. This discussion about humans and machines working together. And there's a couple of questions that have been posted, but I think at least one and maybe two hit on this exact issue: the concern about automation increasing, about machines doing more and more. So sort of what is the role, or what are the roles that humans and some of these people posting these questions, I'm sure our students in say our IMBA program, they may want to say, what are things I should be thinking about augmenting or improving myself so that I can work better with the machines going into the future?
That's right. I think what you should do is just pretend that the stuff that you're learning right now really can be automated. It can't. You have to learn it. You need to know the stuff. And by the way, it's a lot of fun. This is why we're all geeks. We love things like random forest. We love things like machine learning and deep learning. But the thing is, even if it can be automated, you need to understand the principles. Even if I'm never going to do it again in my life, it's good that I learned how to take a square root. I've forgotten how to do it. So you want to learn all this stuff. I'm not trying to say that's not necessary, but just for a minute, pretend that it really was automated. How would I stay employable? It would be to do things like address the first mile problem and the last mile problem. I like to say that data science is a liberal art. My bachelor's degree was actually in liberal arts, and I'm going to admit this now. I didn't know how to use a spreadsheet when Allstate Insurance Company hired me. They took a real risk on me. Okay. But I feel like we need more people like this. We need to treat data science as a liberal art. So Robert, you should be teaching this to more people, not fewer, because like the underwriter and the judge and the doctor should be learning this stuff. Eric Topol in his book Deep Medicine says, far from deep learning replacing doctors, we're going to have Renaissance radiologists who are 1/3 data scientist, 1/3 MD, 1/3 bartender who can empathetically communicate to the patients, right? In analogously with data scientists, we need Renaissance data scientists who understand public policy, who understand regulation, who can, even if they've never worked in child support enforcement before, are intellectually curious and have enough grounding in a broad set of topics so they can have an intelligent conversation with that person. So, Andrew Gelman at Columbia has this phrase that all statistics is consulting. Well, I'd like to say that all AI, all applied AI, or all data science is consulting. So think of yourselves as being liberal arts people. I'll close with John Tukey again. His other favorite quote of all times is, the great thing about being a statistician is you get to play in everybody's backyard. Yeah. The great thing about being a data scientist is this is exactly the same thing. So you get to play in everybody's backyard. So you should want to be a data scientist, not because you're the best person at tuning hyperparameters, but because you're the best people that can use those things as a way of effectively helping your clients achieve their goals.
Yeah, love the response, love the conversation, and I'm sure we could go on and on and on, but I think we're going to get hooked here. So thanks again, Jim. I really appreciated the conversation. Amanda?
Thanks.
Yeah. Thank you, Jim. Thank you, Robert. Your passion for this topic is apparent, and we really appreciate all of your great insights today. Thanks also to our great participants for attending today and bringing some questions to the table. We hope you gained valuable knowledge, and we hope you'll join us next time. Make sure to join our mailing list to learn more about our upcoming events, and we wish you a great day. Thanks again, Jim and Robert.
Thank you.
Thank you. Bye-bye.